Hey there, and welcome to this explainer. Today we're jumping straight into a masterclass on a seriously fascinating subject, input and output devices. We are going to bridge the gap between the messy, physical world we live in and the clean, digital data that computers use. Specifically, we're tackling topic 3.2 to make sure you absolutely ace your upcoming exam. Think of this as your ultimate animated study guide. Let's get to it.
Here's our roadmap for today. Number 1. The Input/Output Foundation. 2. Scanning and imaging devices. 3. Audio and typing inputs. 4. Touchscreen technologies. 5. Sensors and microprocessors. And finally, 6. Monitoring versus control systems. We're building your mental model step by step. All right, Section 1, the Input-Output Foundation. Let's look at how we actually bridge these two worlds.
You've got to remember, computers only speak binary, just zeros and ones. Without these devices acting as our translators, microprocessors would be totally isolated in the dark. Input devices take human actions or physical things like light, sound, or pressure and convert them into digital data. Output devices do the exact reverse. They take that processed binary and turn it back into something you and I can actually see, hear, or feel. It's basically a two-way translation service.
Moving right along to Section 2, Scanning and Imaging Devices. Let's see how light gets translated into data.
We all see barcodes every single day at the grocery store, right? But if you're asked to describe a barcode scanner in an exam, you have to use this exact sequential logic. First, a red laser or LED shines onto the barcode. Second, the block lines absorb that light while the white space is reflected back. Third, that reflected light is captured by photoelectric cells. And fourth, those cells generate a pattern that the computer translates into binary data. Step 1, 2, 3, 4. Lock that sequence in your brain.
Now, QR codes are a massive step up from standard barcodes. Instead of just 1D vertical lines, QR codes use a 2D matrix of light and dark squares, essentially pixels. Have you ever noticed those 3 large squares at the corners? They're absolutely crucial. They act as alignment targets, which lets your smartphone's camera instantly orient the code and read the binary values perfectly, no matter what crazy angle you scan it from.
And speaking of cameras, let's talk about how digital ones actually capture the world. It starts with light passing through the lens and hitting a light-sensitive array called a charge-coupled device, or CCD. This CCD is packed with millions of tiny sensors that convert light into tiny electrical charges. Then the real magic happens. An Analog-to-Digital Converter, the ADC, translates those varying electrical charges into a digital array of pixels, creating your photo. So it goes light to electricity to binary.
Okay, time for some insider exam tips. Examiners absolutely love comparisons, so always contrast the data capacities. Barcodes hold up to 30 digits, while QR codes can hold over 7,000. When you're explaining scanners, dropping the phrase photoelectric cells is practically guaranteed to secure you marks. And don't forget, if you scan a paper document and want to edit the text later, you literally must mention that the software uses OCR, Optical Character Recognition. Section 3. Audio and typing inputs. Let's look at how everyday sound waves and keystrokes do their thing.
We type all day long, but how does the computer actually know what we're pressing? Well, underneath your keyboard is a hidden matrix of circuits. When you press a key down, it physically pushes 2 conductive layers together, completing a circuit. That action sends a highly specific electrical signal to the computer, which it then translates into a digital ASCII value representing the exact letter or number you just pressed.
Microphones are another brilliant example of mechanical movement creating electrical energy. When you speak, you create sound waves that make the air vibrate. Inside the mic, a super-thin diaphragm picks up those vibrations and moves a tiny copper coil back and forth inside a magnetic field. That physical movement induces an analog electric current. Finally, our trusty analog-to-digital converter steps in to turn that continuous current into a crisp digital sound file.
More exam tips coming your way. If you get a question on audio input, failing to mention the ADC is literally the #1 reason students drop points. You absolutely have to bridge that analog sound over to the digital computer. Also, if they ask about an optical mouse, remember, it doesn't use a physical trackball. It actually uses tiny cameras snapping around 1,500 images per second to track movement.
Moving into Section 4, Touchscreen Technologies. This is a big one where you'll often need to compare different setups.
Take a mental screenshot of this cheat sheet right now. You've got 3 main types: capacitive, infrared, and resistive. Capacitive uses the unique electrical properties of your skin.
Infrared relies on you breaking an invisible grid of light beams, and resistive relies on two physical layers actually being pushed together. Each one has its own distinct pros and cons that decide exactly where they get used in the real world.
The absolutely crucial point here is knowing the practical difference between capacitive and resistive screens. Ever wonder why your smartphone, which is capacitive, completely ignores you when you're wearing thick winter gloves? It's because the screen relies on pulling a tiny electrical charge from your bare conductive skin. A resistive screen, on the other hand, like the ones on older ATMs or supermarket checkouts, just needs physical pressure to push its layers together. So a gloved finger or even a plastic pen works perfectly fine.
When answering questions on touchscreens, always link the technology to its real-world application. Resistive is cheap and works with anything, making it super common in retail. Infrared is incredibly durable, which makes it perfect for outdoor public kiosks. And a quick tip on outputs: if you're asked about digital projectors, remember they use a chip called a Digital Micromirror Device, or DMD. It uses millions of microscopic tilting mirrors to reflect light and build the image. Pretty wild, right?
All right, Section 5, Sensors and Microprocessors. This is the brain and the senses of automated systems.
Think of sensors as the nervous system of a computer. They're input devices, constantly taking analog readings from the messy physical world, stuff like heat, light, or pressure. But here's the catch. Sensors do not make decisions. They just feed this continuous analog stream of data straight into the brain of the operation, which is the microprocessor.
In an exam setting, you need to be able to confidently pair a specific sensor type with a logical real-world application. For example, a temperature sensor is obviously perfect for central heating. A photoelectric light sensor, that controls when automatic streetlights kick on at dusk. Active infrared sensors shoot out invisible beams, and when a person breaks that beam, bam, it triggers a security alarm. It's all about matching the physical measurement to the right automated task.
Understanding that setup gives us a universal three-step logic for how computers process any sensor data. Step 1. The sensor reads analog data from the environment. Step 2. Since the microprocessor only understands binary, our trusty ADC has to convert that analog data into a digital format. Step 3. The microprocessor receives the digital data and compares it against pre-stored parameters to see if things are normal or out of whack.
Which brings us to Section 6, Monitoring versus Control Systems, because once the microprocessor checks that data, it has to decide what to do next.
The distinction examiners are looking for here is subtle but absolutely vital. A monitoring system simply watches. If a hospital patient's heart rate drops, the system sounds an alarm to alert a nurse, but it doesn't physically treat the patient itself. A control system, however, actually takes action. It uses a feedback loop to send signals to output devices called actuators. These actuators then change the physical environment.
Here is your final batch of exam tips. You really need to master the concept of the actuator and the feedback loop. If a greenhouse gets too cold, a control system doesn't just beep about it. It sends a signal to an actuator, maybe a motor opening a valve to crank up a heater. Because the heater warms the room, the very next reading the temperature sensor takes will be different. That continuous cycle of reading, processing, and altering the environment is called a feedback loop, and it is the absolute hallmark of a control system.
So, there you have it. You now possess the complete step-by-step logic of input and output devices. You know how the physical world gets translated into digital data and how microprocessors use that data to physically control our environment. So, I'll leave you with this to ponder. As sensors become vastly more sensitive than our own human eyes and ears, and actuators become way faster than our hands, how long until human data entry disappears entirely? Thanks for hanging out with me for this explainer, and best of luck crushing those exams.